Okay. Well, thanks very much for inviting me to participate. So I'd like to start this session by talking about what we can learn about cosmic rays in the disk of the Milky Way galaxy through astrochemical reasoning and based on observations of small molecules. So let me just start with a little bit of history that hopefully will be useful for the whole session. So the cosmic rays were actually discovered a little over a century ago by Victor Hess, who conducted a series of experiments in a balloon for which he won the Nobel Prize in 1936. And here you see him about to leave in this wicker basket. And he went a series of flights up to altitudes as high as 17,000 feet, carrying with him an electroscope, which he used to measure the ionization of the air as a function of altitude. So it was well known that electroscopes gradually lost their charge and their leaves would go down because the air was ionized, but it was believed that the source of the ionization was probably the radioactive decay of materials in Earth's crust. But what Hess actually found is that the ionization rate or the level of ionization of the air increased with altitude, indicating that the source of ionization was of extraterrestrial origin. And these were called cosmic rays, but their nature was very controversial. And there was a sort of vicious debate between Millikan and his former student Compton about whether these were charged particles or gamma rays. So here's a sort of headline from the New York Times in 1932. There's some stories here about the Roosevelt transition team and what Mussolini was doing in Italy, but here in the top left-hand corner is this article reporting the proceedings of a meeting where Millikan was attacking his former student Compton. Millikan believed that the cosmic rays were gamma rays, and he had an almost religious belief for their origin, whereas Compton said they were charged particles. And he described Compton's work as incautious, but whether it was cautious enough or not, we now know that the student was right in this case, and cosmic rays are charged electrons, protons, and other nuclei. And we now know that they exist over a remarkable range of energies, as you can see the energy spectrum in this plot here. The most energetic cosmic rays that have been detected have Lorentz factors of more than 10 to the 11, meaning that a single cosmic ray proton can have as much kinetic energy, 50 joules, as a tennis ball served by Roger Federer in his second serve only, not his first serve. They're also a very significant contributor to the energy density in the galaxy. In fact, one that is slightly larger than that of starlight, the cosmic microwave background, or the galactic magnetic field. So we think of our galaxy as being filled with starlight, but the cosmic rays actually have more energy density than the starlight. These cosmic rays interact with the interstellar gas in a number of interesting ways. The high energy cosmic rays, meaning with energies above a threshold of 280 MeV, create pions, neutral pions, that then decay to produce gamma rays that can be observed and are a very useful probe, as you may know, of the column density of protons along a sightline. But what I want to talk about is the lower energy cosmic rays, which ionize and heat the interstellar gas and modify its chemistry. And so a cosmic ray can ionize a hydrogen atom in a cloud that's mainly atomic, or a hydrogen molecule in a molecular cloud. And there are secondary electrons produced of typical energy about 35 electron volts, and they can cause additional ionization and heating. And also, as was pointed out by Prasad and Tarafdar, can excite UV emissions from H and H2, which are important in dense clouds where starlight is pretty much completely absorbed by interstellar grains. So an obvious question is, what cosmic ray ionization rate would we expect in the interstellar medium given the density of cosmic rays that we can measure, say, in a balloon, as Hess did, or with a spacecraft? And the latest estimates come from observations from the Voyager 1 spacecraft, which has now is at a distance of more than 125 astronomical units from the sun, and has passed into the interstellar medium, where the cosmic ray flux is probably now representative of what is seen in the interstellar medium. As this plot on the right shows, the lower energy cosmic rays are excluded from the inner solar system. So the lower set of points here refer to observations of cosmic rays at 1 AU from the sun. And the higher curve is what Voyager is now detecting. And clearly there's a big so-called solar modulation effect, which due to the sun's magnetic field and the solar wind, which excludes cosmic rays from low Earth orbit and the inner solar system. So based on these Voyager observations, one can estimate the implied cosmic ray ionization rate in the interstellar medium. And the number they get is of order 10 to the minus 17 ionizations per second. There are a few caveats on this. First, the ionization cross-sections actually peak at lower energies than they can measure the cosmic rays. So one has to extrapolate this curve to lower energy. There's also an open question as to whether what one is seeing with Voyager is really completely unmodulated by the effects of the sun's magnetic field and solar wind. And in any case, the results apply only to the local interstellar medium. So then the question is, can we actually infer the cosmic ray ionization rate in clouds in the galactic disk? And the answer is yes, we can do that using astrochemistry and observations of particularly molecular ions that trace cosmic rays. The answer we get, it turns out, depends a lot on what type of cloud you're talking about. So for the rest of the discussion, I'd like to divide things up using the cloud types defined by Snow and McCall in their 2006 annual reviews article. So we're thinking of a progression of clouds of increasing size from diffuse atomic clouds, which are mainly atomic, diffuse molecular clouds that are, say, more than 10% molecular, an intermediate case of translucent clouds, and then the largest and densest clouds, dense molecular clouds, where there's very little atomic content. So this again is from Snow and McCall's review. So if we look at dense molecular clouds, and I think this will be discussed more later on in the session, observations of certain molecular ions, for example, HCO plus, can be used to infer the cosmic ray ionization rate. And the number gotten in one of the studies, but similar results are obtained from other studies, is basically in perfect agreement with the number I gave you previously as being what one would expect from Voyager, 10 to the minus 17 per second. There are also estimates based on the temperature of starless cores, assuming that the heating is due to cosmic rays. They give similar results. So it looked like everything was in good agreement, but then there was a big surprise roughly 2 decades ago, where the cosmic ray ionization rate could be measured now in diffuse molecular clouds using the H3 plus molecular ion, which, as you know, plays a critical role in interstellar chemistry. So in diffuse molecular clouds, H3 plus is produced following the ionization of H2 to produce H2 plus, which then can transfer a proton to another H2 molecule to make H3 plus. And based on observations of H3 plus, and also a new measurement in the lab of the destruction rate of H3 plus by dissociative recombination, McCall et al. Inferred an ionization rate towards, in clouds along the sightline to zeta Per, of 50 times larger than what is inferred in dense molecular clouds. And this was followed by many observations, and particularly a study by Indriolo and McCall, where they measured H3 plus in many clouds and estimated the average cosmic ray ionization rate as 1.5 10 to the minus 16 per second. So this suggests then, if you believe all this, that the cosmic rays are excluded from dense clouds by shielding, and that the rate in the diffuse clouds is therefore higher. Most of these analyses basically use simple analytic approximations to the chemistry. And we revisited this, Mark Wolfire and I did, with detailed models for diffuse clouds. And we basically got a similar result, but one thing that we did observe was a marginal detection of a decrease in the ionization rate inferred with the column density through the cloud as measured from observations of H2, which is shown in these plots. So, and if you extrapolated this, you would drop by roughly a factor 20 by the time you got to a dense cloud. So that would be sort of a consistent picture. So based on these slightly more detailed models, we basically got a mean value for the cosmic ray ionization rate of 2.3 10 to the minus 16 in diffuse molecular clouds. So these are clouds where H2 is more than 10% of the total hydrogen content, but still C plus is the main reservoir of gas phase carbon. So the question is, can one probe further to the left in this table and look at diffuse atomic clouds? And we've been able to address this through observations of other molecular ions that are most abundant in diffuse atomic clouds. So these are more than 90% atomic, and the ions that we observed are OH plus, H2O plus, and argonium, ARH plus, all of which are produced in reaction sequences that are initiated by cosmic rays. And so there's a pathway following the cosmic ray ionization of a hydrogen atom to OH plus and H2O plus. And then with models, we can compare the observed values of various abundance ratios that are shown in this diagram with the predictions of a grid of models with different ionization rates and different cloud sizes as measured by the total visual extinction. And we adopted as our data set some observations of diffuse clouds from Herschel, where we observed bright continuum sources at large distances in the galaxy and could measure the abundances of these molecules through absorption line spectroscopy. We were also able to observe argonium, which traces gas of that is almost purely atomic because it's very rapidly destroyed by H2. But again, its production is initiated by cosmic ray ionization, in this case, the ionization of argon atoms. And so combining these results, we obtained an estimate that was almost in perfect agreement with the estimate for H3 plus of about 2×10⁻16 for the cosmic ray ionization rate in the galactic plane in the diffuse interstellar medium. So this slide sort of summarizes these various estimates in the different cloud sizes. And so the summary then is that two independent methods of estimating the cosmic ray ionization rate through observations of molecular ions give numbers between 2 and 2.5×10⁻16. This is a factor of 20 larger than that estimated for dense clouds in the galaxy, suggesting that the cosmic rays are excluded from dense clouds. And finally, this cosmic ray ionization rate in diffuse clouds is a factor of 20 or so larger than what you would estimate based on the latest Voyager measurements of cosmic rays in situ using the Voyager 1 spacecraft. So in the future, I did want to just mention observing program that has been approved now for Sophia, where we will observe a number of molecular ions along many more sight lines than we had observed with Herschel Hi-Fi. And with the GREAT instrument, it's actually possible to observe simultaneously all of the 3 molecular ions that I mentioned as being good probes of diffuse atomic clouds. We'll be observing these molecules towards 25 continuum sources with a much wider range of galactic position than what we had done with Herschel Hi-Fi. This is about an 82-hour Sophia program that's now been approved for cycles 8 and 9. And we'll address the questions of how the density of low energy cosmic rays varies within the galaxy, to what extent it varies statistically on small scales or systematically with galactocentric distance and gas column density. So I'll leave it there and now be happy to answer questions.
Great, thanks, David. So as a reminder, everyone, if you go to the bottom of your Zoom screen, you can click the Q&A button and you can submit questions that way. For any questions, and I'll read them off here. Again, if you came in later, feel free to submit whether you would like your name mentioned with the question or not, or if you'd like to keep it anonymous. So we actually have one question here. And it says, are the uncertainties with the cosmic ray ionization rate reliable? And how reliable are they? This may determine what extent we should trust the trend found between the different types of clouds.
Yes. So the errors that I gave are basically statistical errors based on the accuracy to which the abundances of these molecules are determined. And so then, there's a question, okay, but this is all in the context of a model, and how trustworthy is the model? And one can look at some of the rate coefficients that are adopted in the model, and there's some uncertainties there. So it's a little hard to give an estimate of what the possible systematic uncertainties could be. But I think there's pretty good evidence for this trend that we saw when we observed the H3 plus. I mean, statistically, that's a 3 sigma result. And I think this order of magnitude difference between the diffuse and the dense clouds can be regarded as reliable because there are multiple independent ways of estimating the cosmic ray ionization rates in diffuse clouds and independent ways of measuring them in dense clouds. And none of those independent estimates had anything like an order of magnitude variation. So I could have mentioned also in diffuse clouds as yet a third independent way of doing this, looking at the ratio of hydrogen to carbon radio recombination lines. That gives roughly the right answer. And then in the dense clouds, these canonical numbers of 10 to the minus 17 for the primary rate per hydrogen nucleus are established by multiple chemical tracers by the temperature of dense cloud cores. So in my mind, there's no question about that order of magnitude difference.
Great. So I think we probably got time for about maybe one or two more questions. Here we have one. Do you have any wishes for laboratory spectroscopists to measure more spectra for molecular ions? Anything, any specific wishes or anything? Target species?
So nothing that I am aware of in this. I mean, we have very good spectroscopy, I would say, at this point on all of the molecular ions that I've referred to here. As a more general question, I'd rather not shoot off the top of my head. I mean, there are many interesting things that could be done, but I want to consider that in more detail rather than just tell people to go measure things, because I know how hard these measurements are. In terms of the the other data, non-spectroscopic data, but reaction rates, I do know that one thing that's of considerable interest for this is the charge transfer rate for O plus and H, and the back reaction or the forward reaction, where there are some discrepancies in the calculations, particularly in regard to the rates of reaction for the specific fine structure states of O1. And I know some of this is underway in Phil Stansel's group. But yes, I mean, that's an area, I mean, if you wanted to embark on that, it'd be important to find out what other people are doing, because I know, work is underway in at least one group on that.